Now, welcome to another aspect on set theory. Welcome to another aspect on set theory. Now, what is set theory? Set theory is just collection of well-defined objects. That is, the objects that has the same property, that have the same properties. Now, the set theory was initiated by George Cantor in the year 1870s, and that's 19th century. Now, in the year 1870s, that's when George Cantor initiated the word set theory. That is, and as the set is concerned, we have this to be objects that have the same properties. What did I mean by that? Now, when you have the judge does not have E. It does not have E at the back. Don't mix it up. Now, it's observed that we can categorize objects into different aspects. Like, for instance, if you belong to a particular school, you know that you are in that school with the same property with those that are in the same school with you, and you are different or you are different from people of different school because you have different properties. Now, if there is an argument, you have to stay by your school because you belong to that school. That means you possess the same property with that school. That means you are a set of that school. That's why they normally say, are you a set of this school? Yeah. Are you part of the set of this school? That's it. Now, and at the same time with others, they also belong to that category. Now, that's what they mean by set. And within the school as well, we still have subsets. Now, we have different levels. And each level we have more spirits, or let me say more properties, very related property compared to other levels. Now, let us continue. Set is listed inside a bracket called curly bracket. Set is put, the element of a set is put inside a bracket called curly bracket, and there is the symbol. This is the curly bracket. Now, if you have this as the curly bracket, the next aspect we'll be talking about is the fundamental examples of sets. Fundamental example of sets, the first one we'll be talking about is set of natural numbers. Natural numbers is n. Before I talk about this, let me talk about, or let me continue. We have to know that set of natural numbers, and natural numbers is n. If you're talking about natural numbers are just positive, I can say they are positive integers. Or I say positive whole numbers. Natural numbers are numbers which we can regard as positive integers or positive whole numbers. What am I talking about? Example of this. We can have 1, 2, 3, 4, 5, 6, 7, 8, etc. Any positive whole number is known as natural number. Number 2. Now, if I said natural numbers are positive integers, now what are integers? Integer number is denoted as z. Natural number is denoted as n. Integer numbers are just both positive and negative whole numbers. Both positive and negative whole numbers. I can say, for instance, I have -5, -4, -3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, etc. So the integer numbers are both positive and negative whole numbers. Now this is where I'm going. If you look at something here, let me quickly talk about a graph here. If you are talking about a graph, we have a graph to be, if you have a graph from minus 5, minus 4, minus 3, minus 2, minus 1, I have 0, I have 1, 2, 3, 4, 5. I can say this positive side represents set of natural numbers. Don't forget, as I explained, that natural numbers are what? Are positive whole numbers. But the combination of both negative and positive whole numbers here indicates what? Indicates integer numbers. That shows that natural numbers are integer numbers. Yes, because as you can see that all the members of natural numbers can be found in what? In integer numbers. All the members of natural numbers can be found in integer numbers. Now, number 3. Number 3 is set of rational numbers. Rational numbers is noted as Q. When we are talking about rational numbers are in form of A over B. Don't forget, this is numerator. And we have this to be what? To be denominator. Now, natural numbers will be in form of, this. Now, both A and B here, they are integer numbers. Both A and B are integer numbers. Now, this is the funniest thing about rational numbers. Now, don't forget that integer numbers, all natural numbers, they are inside what? They are integer. They are inside what? Integer numbers. That shows that this A and B must be either negative whole number or positive whole number. That's it. But take note, the B, the denominator is the B. This B must not be equal to 0. B must not be equal to 0. Because if B is equal to 0, if you have any number here, if you have 3 over 0, it will give you 0. You get it? It will give you, or let me even say the mathematics error. So it must not be equal to 0, so that it must have what? It must have a value. Now, whenever you are now talking about the rational numbers, I can say categorically that integer numbers, they are under the integer numbers, are under rational numbers. A form of whole numbers are under rational numbers. And don't forget that natural numbers are under what? They are under integer numbers. Because both of these are whole numbers. Either natural numbers or integer numbers, they must be what? They must be whole number. Don't forget. And this natural numbers is under integer number. And I told you that each A and B here must be what? Must be integers. Can you see that they are inside? Now let us see. Let us see an example. That shows that I can say that example here can be equal to, I can have 1 over 4. I can have 3 over 6. I can have 7 over 14. I can have minus 5. There's tendency that I have minus 7. I can have 2. I can have 8. Let me stop it here. Now, if you observe this very well, you observe that majority of the number that you have here, they are rational numbers. Some people will tell me that how will this minus 5, minus 7 be rational numbers? How will these 2 be rational numbers? Then let me prove it to you. You have to understand the fact that if you say something like this one, at least this one explains the rational numbers. It has numerator and what? And denominator. This is rational numbers. Even I can tell you that the rational numbers can also be something like, if you have something like this, let's say you have minus 25 over 5. Minus 25 over 5. You have numerator here, you have denominator. Minus 25 over 5, if you don't know, it will give you what? Minus 5, which is this. Can you see that it is what? It is rational numbers. Even I can have minus 49 over 7. Minus 49 over 7 will also give you what? Will also give you minus 7 here. Can you see now? So this minus 7, can you see the way it becomes a what? A rational number. Can you see the way it is a rational number? Now you just have to understand the fact. Even these two I can say 6 over 3. 6 over 3 will give me 2. I can say let me say 16 divided by 2 as well. 16 divided by 2, 16 over 2 will also give us what? 8. So these are rational numbers. Can you see that it is numerator over what? Over denominator. So they are rational numbers. But don't forget that all the members of these natural numbers can be found in what? In integer numbers. Now can you now notice that all the members of these integer numbers can be found in what? In rational numbers. But example of this one cannot be found in this. Are we all together? Cannot be found in this. Now, let's see other aspects. Number 4. Number 4, we have sets of real numbers. I'm going to explain this number 4 with number 5. Sets of real numbers, and we have what you know as complex number. The denotation of complex number is C, and real numbers we have it to be R. Now, real numbers comprises of both rational numbers and irrational numbers. Both rational numbers and irrational numbers. But don't forget that a number, if you see a number like this, we have 5 plus 3i. Have you seen a number like this? 5 plus 3i. This comprises of real number, and we call this imaginary number. This imaginary number, we can say it is complex. Though we can say all is complex, but the reason why it is complex here is because of the sign of this I. And that shows that the complex number are the numbers in form of a plus bi. These are complex number, a plus bi. But real numbers, the reason why I said no, don't forget that example of rational numbers can be natural number, can be what? Can be integer numbers. Don't forget. But now, if you have something like don't forget, I've explained under this aspect. Under this aspect, I explain what they mean by rational number. Now, I told you that it's comprised of integers and also what? Natural numbers. If you check this very well, you observe that I told that the real numbers comprise of rational numbers and irrational numbers. What is rational numbers? What is irrational numbers? Don't forget, under this example of rational numbers, we can have something like, let's say, we have 3 over 4. 3 over 4. We can have 15 over 100. These are still, we can still have something like minus 5. We can have minus 10. We can have 20. We can have 15. These are what? These are examples of rational numbers. But if you are talking about irrational numbers is opposite of rational number. What did I mean? You don't forget that in this case of rational numbers, I said you have a over b, but this a must not be equal to what? This b must not be equal to 0. But in the case of irrational number, it is not equals to a over b. They are not equals to a over b. In what sense? If you have example of root 2 now, root 2 cannot give you a rational number. It's not rational, because root 2 on the calculator, you can only have it to be, let's say, it will not give you a rational number, that is the numerator of a denominator. Can I say root 2 is 1.4142 etc. Now if you check this, unlike if you have under the rational numbers, I can have something like root, under these rational numbers I can have root 9. Don't forget that root 9 can be equal to 3, and this root, that's 3, this 3 I can have it to be, let me say, 6 over 2. 6 over 2 will give me 3. Can you see? Fraction, numerator over denominator. 6 over 2 can give me 3, and root 9 can also give me 3. So that means this root 9 is what? Is rational number. But root 2 will not give us rational number. So it is what? It is irrational number. That is why irrational numbers are used under the sword, square root of integer numbers. Now, if you have root 5, the same thing with root 5. Root 5 will not give you rational number. That's it. And that's why we call these real numbers. So that means I can have the example of this real number. Let me write this. Both rational numbers and irrational numbers. I can have 3 over 4. I can have 15 over 100. I can have minus 5, minus 10, 20. I can have 15. I can have, let me say root 9. I can have root 3. I can have root 2, that is irrational numbers as well. Even I can have decimal number, that's 0.5, because you can see I can still have 1.14 or 1.41 etc. Can you see? It gives us decimal number. But if you observe very well that we have rational numbers to be all these are rational numbers, but there is an exemption of this that are not part of the words of the rational numbers. Now, if you observe that from onset, from the beginning, we have, from these natural numbers, we have elements of, all the elements of natural numbers belong to what? Belong to integer numbers, which is this. But there are some part of the integer number that does not belong to natural numbers. And we have all the elements of integer numbers that belong to what? To rational numbers, according to my statement, like this one and this. But we have some part of the rational numbers that does not belong to the integer numbers. And we also have all the elements of rational numbers, like these ones, this, that belong to what? That belong to rational numbers. All the elements of rational numbers, which is everything here, they belong to real numbers here. But example of these ones, they are parts of irrational numbers, which are not part of what? Rational numbers. So there are some elements of real numbers that are not part of what? Of rational numbers. And lastly, we have the example of complex number. I told you that complex number in form of a plus bi. Example, you can have, I told you that they are under imaginary. Now if you have something like, you can have 5i, you can have 3i, you can have 2i. Now if you express this to some reasonable extent, you can have decimal number 0.5. Even you can have roots of minus 6. Roots of minus 6 will give you, don't forget that I, take notes, I value is root minus 1. I value, I, whenever you see I in any number, is equals to root of minus 1. That's the value of I. We have this to be, even you can have a complex number to be 7 plus 6i. The presence of the I shows it is what? It is decimal number. It is complex number. Now if it's chi, if you see this, I can have root minus 16. Because root minus 16, on a particular day, I can have root minus 16 to be equal to root 16 multiplied by root minus 1, according to the law of the sword. Root 16 multiplied by root of minus 1 will give me roots of what? Roots of minus 16. Roots of minus 16. Yes. Because Don't forget that I can split this to root of minus 1 plus 16 and multiply by 16. And if I split this will be root minus 1 multiplied by 16. So now, if you observe very well, and I told you that this root minus 1 is equals to what? Is equals to I. So I can definitely say root minus 16 is equals to root 16I. Root 16I is the same thing as root minus 16. And don't forget that I can have all this is 0.5. All this decimal number is 0.5. You can have 1.72. All these numbers, they are what? They are example of what? Of real numbers. Don't forget the example of real numbers. But we can have example of this I, the presence of this I, these ones, which are the what? Which are the complex number, and they cannot be found in what? In real numbers. And that gives us a formula that says natural number is a proper subset of integer numbers. Integer number is a proper subset of rational numbers. Rational number is the proper subset of complex number, of real numbers rather. And real number is a proper subset of complex number. What am I talking about? It means that all members of natural numbers can be found in integer numbers, but not all members of integer numbers can be found in natural numbers. All members of integer numbers can be found in rational numbers, but not all members of rational numbers can be found in integer numbers. All members of rational numbers can be found in real numbers, but not all members of the real numbers can be found in rational numbers. All members of real numbers can be found in complex number, but not all members of the complex number can be found in real numbers. So that is the example. Now let us take a look at some numbers and let us see.